In this video, we will learn about the quotient rule. So in section 2.4, we have two rules. We have the product rule and we have the quotient rule. The product rule tells us how to differentiate a product of two things that both involve variable quantities. The quotient rule tells us how to differentiate a quotient of two things that both involve variable quantities. So this is only applicable when the numerator and the denominator both have variables in them. So here's what the quotient rule says. In the product rule, we use U and V. In the quotient rule, I'm going to use N and D for the formula for the numerator and the denominator. So if N and D are both functions of X, so what that means is that if the numerator and the denominator both have variable things, like they both have x's in them, then if you want to differentiate n over d, stuff with x over stuff with x, so find the derivative, so I'll just put a prime here, then the formula for calculating this is another quotient. In the denominator of the derivative, it stays the same except we square it. So there's no differentiating in the denominator, we just end up squaring the denominator. In the numerator, what we get is the denominator times the original numerator's derivative, then minus the numerator times the original denominator's derivative. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom. So the numerator here looks kind of similar to the product rule, except with a minus between instead of a plus. But it doesn't matter in this situation. It's very specific that the denominator comes first and then times the numerator's derivative. And this makes a difference because we have a minus between them. And if you swap it around, then you'll get the negative or something different. So some notes about the quotient rule. The first note is that this means if we're going to differentiate a product, this is not going to be done by finding the derivative of the top and putting it over the derivative of the bottom, unfortunately. It would be so nice if that were the case, but it is not. The second note is that this is only needed when the numerator n and the denominator d are variable quantities. So again, that means when there are variables in the numerator and the denominator, like x's, not constants. If either the numerator or the denominator are just constants, then we can use an easier rule. So if the denominator is just a constant, we want to break that out and look at it as a constant multiple with a fraction. If the numerator is a constant and we have variable stuff in the bottom, we will actually learn another rule that will work in more cases. So we'll talk about that then. The third thing to note is that sometimes algebra first is easier than using this rule. So if we have a quotient that we can simplify and get rid of the fact that it's a quotient by using algebra, then that's probably an easier way to go about the problem. So for example, if we have a function that looks like 3x squared minus 4x divided by x, you could absolutely use the quotient rule on this. However, I'd recommend that you rewrite this first to get rid of the quotient, because the quotient rule is probably the most complicated rule that we will have for differentiating. So by rewriting, we can think of this as instead of the whole thing in the numerator divided by x, we can break this down into 3x squared over x minus 4x over x. And then we can cancel out the x's in each of those individual pieces. So the 3x squared divided by x is just 3x. And then the 4x over x is just 4. So then we have this thing that's equivalent to 3x minus 4. And then we can just differentiate this and avoid using the quotient rule. Again, it wouldn't be wrong to use the quotient rule on this example, but it will be a lot more work than if you were to just kind of be smart about it first and say, okay, I'm dividing by a single thing in the bottom, so I can kind of rewrite this first and then use our simpler rules. So in our first example, let's look at differentiating the function 2x cubed divided by 1 minus x squared. So in the example in the note that we just looked at, we were dividing by a monomial, a single term, just x in the bottom. When that's the case, you can often split up and try to cancel or simplify to avoid using the quotient rule. In this example, we have in the denominator a binomial. It has 2 terms. When that's the case, there's nothing that you can often do to simplify and avoid using the quotient rule. So let's get started identifying what is the numerator and what is the denominator. All right, so the numerator, of course, is the 2x cubed. So we'll call that n. And the denominator is 1 minus x squared, so that's the d. Now in our formula, we're going to need n prime and d prime. So the derivative of each of the pieces, on the top, we've got 2x cubed. So the derivative of that, we'll bring the 3 down and multiply by the 2, so that's 6, and then we'll subtract 1 from the power, so 6x squared. Then our denominator's derivative will be the derivative of 1, which is 0, minus the derivative of x squared, which is 2x. So it'll be minus 2x. Okay, so then we can put this together into the quotient rule formula. So we'll find the derivative of the entire function. So we have the bottom, the denominator, which is 1 minus x squared, times the derivative of the numerator, which was 6x squared. Then we're going to subtract the numerator, the top, which is 2x cubed, times the derivative of the denominator, which is negative 2x. And then that all gets divided by the square of the original denominator. So 1 minus x squared, whole thing squared. So this is the end of our calculus part to this problem. The rest of this is just going to be simplifying using algebra. So in simplifying this, the numerator should always be simplified. So always expand this out, maybe factor if you can, in the very end. So that's where most of our work will lie. In the denominator, you never want to expand this out. In this case, FOIL. Never FOIL or expand. In general, you're never going to want to do that. A factored denominator is the best denominator to have, and this is already nice and factored, so we can leave it as it is. So in the numerator, let's work on simplifying that. So let's distribute the 6x squared into the 1 and the x squared. So it'll give us 6x squared minus 6x to the 4th. Then we have minus the product of 2x cubed times negative 2x. So that'll give us a negative 4x to the 4th, but we're subtracting that, so it'll become plus. And again, we're going to leave that denominator exactly as it is, just 1 minus x squared squared. Now in the numerator, we have some like terms that we can combine together, the x to the 4ths. So negative 6x to the 4th plus 4x to the 4th will give us negative 2x to the 4th. And so this is usually a good place to stop unless you can further factor the numerator. I think in the numerator we have a GCF, or greatest common factor, of a 2x squared that we could pull out. When we do that, we'll have a 3 left with the 6x squared. And when we factor out a 2x squared from the 2x to the 4th, we will have a 1x squared left. And then again, the denominator is going to stay as it is factored. Now, finally, what you can do is look and see if there are any similar terms or like same terms in the top and in the bottom that we could cancel. In this case, we don't have anything that we could cancel by dividing, so this is fully simplified. So here's our fully simplified derivative. The quotient rule tends to give kind of complicated derivatives, and that's okay. So most of our work is going to lie, again, in simplifying the numerator. So here's an example number 2. I'd encourage you to pause this and try this one on your own by using our quotient rule formula. So the first step is to identify what the numerator and the denominator is. That's usually not too hard. Right, here's the numerator and here's the denominator. Now in our quotient rule, we're going to need the derivative of the top and the derivative of the bottom. So I just like to keep track of this over here, but if you don't want to, you don't have to. The derivative of 4x squared is 8x. Bring the 2 down and multiply. Subtract 1 from the power. Then we'll add the derivative of 7x, which is 7. Subtract the derivative of 5, which is 0. Then the derivative of the denominator, we'll bring the 2 down and multiply the other 2 to give us 4. Subtract 1 from the power, so 4x to the first. Okay, so we are all set now to find the derivative of the entire function. So this will be g prime of x. We just need to put all these things together into the quotient rule. So we'll do the denominator times the derivative of the numerator, right? And it's all in this big quotient here. So we have the bottom times the derivative of the top, which was 8x plus 7. Okay, so this is d times n prime. Then we subtract n times d prime, the top times the derivative of the bottom. Okay, so this is n times d prime. Then in the quotient rule, our whole denominator becomes squared. So we'll square 2x squared squared. Okay, again, this is the end of our calculus part of this problem. Now we just want to simplify. So again, to reiterate, here we're going to simplify in the numerator. Now I said never FOIL or expand out the denominator, but here our denominator wouldn't need to be FOILed to kind of simplify it. So it probably is a little bit better in this case when we have a single term in the bottom to multiply this out. So that's not too bad in the bottom. We'll square 2x squared. So we've got to square the 2, which gives us 4, and we've got to square the x squared. It'll give us 4x to the 4th. On the bottom, we just have a lot of expanding to do and combining some like terms together. So we'll distribute the 2x squared into the 8x and the 7. So it'll give us 16x cubed. Then plus 14x squared. All right, then we're going to subtract what we get when we distribute the 4x into here, here, and here. Sorry, so it might not be a bad idea to just kind of leave parentheses around this first. 4x squared times 4x is 16x cubed. 7x times 4x is 28x squared. And 5x times 4x is 5 times 4x is 20x. And then lastly, we should probably get rid of these parentheses by distributing the minus sign into here, here, and here. Okay, so that's 16x cubed plus 14x squared minus 16x cubed minus 28x squared plus 20x. Again, that is all divided by 4x to the fourth. All right, I see some x cubes that we could simplify. They actually are the same, so those will just cancel out or add up to 0. I see some x squareds that we could combine together. 14x squared minus 28x squared will give us negative 14x squared, I believe. And we still have plus 20x. Okay, now the last thing you want to do is see if you can factor the numerator, because sometimes you can cancel with things in the denominator. So I think we have a GCF up top of a 2 and an x. So let's factor that out. What we'll have left is a negative 7x and then plus 10. That's all over 4x to the fourth still. Now because this is multiply here between the 2x and the parentheses, we can simplify with the denominator. So we could cancel out a 2 up top, and we'll have a 2 left in the bottom. We can cancel out an x here, and then it'll leave us with x cubed in the bottom. So at the very end, what we'll have is negative 7x plus 10 all over 2x to the third. That's as simplified as our derivative can pretty much get. Now, one option way back in the beginning, what we could have done is rewrite this without a quotient, like I was mentioning in our notes before about the quotient rule. If you wanted to, what you could do is divide each of these pieces, 4x squared and 7x and negative 5x, by the 2x squared, and then get rid of the fact that you have a quotient, and then use a simple power rule. That'll give you something that isn't a single fraction. That's okay in the end. But again, I was just kind of using this as an example for the quotient rule. Okay. One last example here with an application. So here we have a function that models the temperature, capital T, in degrees Fahrenheit of food placed in a refrigerator. And it's modeled by this long equation. It's capital T equals 10 times 4t squared plus 16t plus 75, all divided by t squared plus 4t plus 10, where little t is the hours since the food was placed in the fridge. So part A asks us, what is the initial temperature of the food? Part B asks, find the rate of change of the temperature after 1 hour and after 10 hours, and interpret. Okay, so in part A, there's actually no calculus that we're asked to use in part A. The initial temperature of the food, we're not asked to find the rate of change. We're just looking for the actual temperature. So in part A, we're just plugging in 0 for T, right? The initial temperature means right when the food is placed in the fridge. What is the temperature of the food? So we're just going to plug in little t is equal to 0. Okay, so in other words, capital T of 0. So we'll have 10 times 4 times 0 squared plus 16 times 0 plus 75, all divided by 0 squared plus 4 times 0 plus 10. And notice everything kind of is just 0, 0, 0, 0 here. So what we're left with is 10 times 75 over 10. Those 10s just cancel out, and we get 75 degrees Fahrenheit. All right, so this food is probably sitting out at room temperature, and that's what the temperature of the food is right when it's placed in the fridge, 75 degrees Fahrenheit. Of course, over time, the temperature of the food is going to decrease as it is placed in the fridge. So let's see how the temperature is changing over time at a couple different points in time. So in part B, okay, we're looking at the rate of change of T after 1 hour and after 10 hours. So this is an instantaneous rate of change, two separate ones at two different times. Okay, so we have instantaneous rate of change, or IROC, I-R-O-C, right? And remember that this is the derivative. Instantaneous rate of change means derivative, so in this case, capital T prime. So it looks like we're going to need the quotient rule to differentiate this. So let's see. In our function, our numerator is this 4t squared plus 16t plus 75. Our denominator is this t squared plus 4t plus 10. And then out in the front of everything, we have this 10 here, and this is actually a constant multiple. So remember, when we differentiate a function, a constant multiple out in the front can just stay out in the front and multiply by the derivative of the variable stuff that it's multiplied by in the function. So the derivative of the numerator, and we're going to need that for our quotient rule. So we have 4t squared, that's derivative is 8t to the first. Then we'll add the derivative of 16t, that's plus 16. And then we'll add the derivative of 75, and that is, of course, 0. So here's n prime 8t plus 16. Now our denominator's derivative, or d prime, the derivative of t squared is 2t. Then we'll add the derivative of 4t, which is 4, and add the derivative of 10, which is 0. Okay, so let's put this all together to find the derivative of capital T. So the 10 is going to stay there and multiply by the derivative of this quotient that we have, which we're using the quotient rule on. So I'll like set a big parentheses here, and this will be our quotient rule derivative. So let's see, we're going to have a big fraction, and it will be the bottom, the original bottom. Now look back in your notes at the quotient rule formula as we're putting this in. So it's the bottom times the derivative of the top. D times n prime. Then it's minus the top times the derivative of the bottom. And this is all divided by the original denominator, whole thing squared. That's a massive derivative. So, but take a second to just look at this, pause it, and see if you know where each piece is coming from. Right, here's the denominator, d, here's n prime. Then we subtract n, the numerator at the top, times the bottom derivative, times b prime. And this is all over the original denominator squared. Now you could just plug in the hours that we're looking for, the rate of change at. You could also simplify this. So I know it looks really complicated. It's probably more complicated than anything that I'll ask you to do on like a quiz or anything like that, but it's actually not that bad if we just take some time to just distribute some things kind of carefully. So foiling is really like double distributing. So what we're going to do is just take everything in this 3-term polynomial and distribute it into the 8t plus 16. So we'll do t squared times 8t, and then t squared times 16. So just, again, we're working on simplifying the numerator here. So let's start with that. So we still have a 10 in the front. We're still going to leave the entire denominator fully factored. Don't bother foiling that out. We want to kind of expand the numerator and see if we can combine like terms. That's the idea with that. So if we distribute the t squared into the 8t and the 16t, we'll get 8t cubed plus 16t squared. Then we've got to distribute the 4t into the 8t and the 16. So that'll be plus 32t squared plus 16 times 4. What is that? 64? 64t, yeah. Then we will distribute the 10 into the 8 and the 16. So it'll be plus 80t plus 160. I think I'm going to need a bigger fraction here. So let me, maybe let's just move this over a tiny bit. Okay, then we will subtract what we get when we distribute the other 3-term polynomial times the 2-term polynomial. So let's put a big set of parentheses here so we don't forget to distribute the minus sign. So let's distribute the 4t squared into the 2t and the 4. All right, so that is 8t cubed plus 16t squared. Then we'll distribute the 16t into the 2t and the 4. So that'll be plus 32t squared plus 64t. Then we'll distribute the 75 into the 2t and the 4. 75 times 2, I'm going to need even a little more space here. 75 times 2 is 150. And then 75 times 4 will be 300. I think that's the end, so big parentheses to end that. Okay, rather than write all of this over again, the last thing we're going to want to do is distribute that minus sign into this whole set of parentheses on the second part of the numerator. So let's just kind of do this without rewriting. So we're going to distribute this minus sign. So let's do it. That'll end up being a plus. Then we'll just change the sign of everything in between. So it'll be minus 8t squared, minus 16t, minus 32t squared, minus 64, minus 150t, and then minus 300. And I think a lot of things are going to cancel out. We've got 8t cubed minus 8t cubed. We've got 16t squared minus 16t squared. We've got 32t squared plus minus 32t squared. Oh my gosh, we've got 64t minus 64t. I think that's all it's going to actually just add up to 0. And there'll be some like terms together that we can combine. So we've got 80t minus 150t. Those combined together will give us negative 70t. Then we've got 160 minus 300. That combined together will give us minus 140. That's pretty nice. Right after all that work, it's kind of worth it to simplify to such a simple thing. In the bottom, like I said, we never, ever, 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 ever want to distribute or FOIL out that denominator, so we can just leave it like this. Okay. If you wanted to, you could distribute the 10 into the numerator. No need. We can just leave it as it is. So what do we want to do? We want to find the rate of change now after 1 hour and after 10 hours. So we're going to plug in a 1 for little t. And see what the rate of change is. So t, capital T prime of 1. So we'll plug in a 1 for little t. So we'll get negative 70 times 1 minus 140. And then that's all over 1 squared plus 4 times 1 plus 10, whole thing in the denominator squared. This is a lot to put into your calculator all at once. So make sure that you are comfortable plugging this stuff into your calculator. Like actually go get it and try this out. And if you're not, please come to me and we can definitely work through with your specific calculator how you might handle something like this better. I would suggest probably getting the numerator simplified first, then getting a number for the denominator, and then doing it like kind of piece by piece like that. But when you do calculate this as a decimal, you're going to get negative 9.33333 repeating. So we'll leave that as negative 9.3 with a bar up top. Now remember from section 2.3, our section on rates of change, that the derivative units will end up being the units of the output of the original function, so the temperature, which is degrees Fahrenheit, over the units of the input. Little t is measured in hours. So degrees Fahrenheit per hour. Let's think about what this means. So the fact that this rate of change is negative makes sense because the temperature is decreasing, right? It's losing degrees, it's getting colder. The per hour isn't for every single hour. This is the rate of change just at the first hour. So the way that we would interpret this, as we would say in the first hour, actually, it's not really the first hour. The first hour would be from 0 to 1. So let's just say more specifically from t equals 1 to t equals 2. So in other words, in the second hour, after the food is placed in the fridge, the food's temperature decreases by approximately 9.333 degrees. Okay, so in the second hour from t equals 1 to t equals 2, the rate of change is about negative 9.3 degrees Fahrenheit, which means that the temperature will be decreasing. Okay, from at t equals 10 hours, so 10 hours after it's placed in the fridge, you would imagine that the temperature is going to be closer to like the temperature of the refrigerator, right? It will probably be decreasing less in its temperature because it will be closer to the temperature of the refrigerator. But let's see what the math says. So we're going to find t, capital T prime of 10. So we're going to plug in a 10 for little t. Again, make sure that you're comfortable plugging something like this into your calculator. I'm just putting in a 10 for little t. And when you calculate this, you get negative 0.37 and then 33333 repeating. So we'll put a bar above the 3. And again, the units for this is going to be degrees Fahrenheit per hour. Again, this isn't every hour. This is just for the hour that we plugged in, just for the hour starting with 10. So from little t equals 10 to little t equals 11, which would be in the 11th hour, right, the temperature of the food decreases by about 0.373 degrees. Again, which makes sense. It's still negative, it's still losing temperature, it's still getting colder, but it's not getting colder as quickly because it's been in the refrigerator for longer. Okay, so this is the end of our examples for the quotient rule. I know that there aren't many here, but I do think that it will just take a lot of practice on your own to be comfortable using the quotient rule. So I encourage you right now to go try some on WebAssign on section 2.4 along with the product rule. And if you are done with that, you can go and look at your written homework, which the last few questions on your written homework are asking you to use the quotient rule and the product rule to find the derivative of some functions. Next week, we will learn, I know I told you this was our last derivative rule, but we've got one more, which we'll talk about next week, and then get into a little more applications into physics stuff. So I hope you have a good week, and I'll see you then.